So that's where we begin, is with just constant velocity motion. But then we're going to start to add some acceleration. So to do that, I'll take our track and just lift up one end a little bit. And now we see that when I let go of the cart, it gradually speeds up. That's acceleration. And it slows down on the way up. So this idea that something can gradually accelerate, gaining speed, and then decelerate, losing that speed, okay, that's accelerated motion, also part of kinematics. In chapter 3, what we're going to do is we're going to take it into a whole different dimension, the second dimension. Instead of one-dimensional motion along a line, we're going to look at motion in a plane. Okay? And so one example of motion in a plane that we'll take a lot of time looking at is what we call projectile motion. A projectile is anything that is thrown through the air, right? So I take this tennis ball and I throw it. It's not just moving in a line. Now you see that it's actually moving in an arc, right? It's a two-dimensional plane. As we talk about forces, we'll look particularly about how forces cause accelerations. So for example, if I have a cart here, I can go and apply a very small force to this cart. I'm just going to push it with a very light, constant force. And if I do that, just applying a constant force, what we see is the cart accelerates. It gradually speeds up as I continue to apply that constant force. I'll do that once more, right? So I start, and I'll get myself spinning kind of slow. Okay, and now I pull my hands in, and I suddenly go much faster, right? That's pretty neat. That's actually due to the conservation of angular momentum. In chapter 6 and 7, we're going to study energy and momentum. In particular, we were looking at the conservation of energy and the conservation of momentum. And you can get a particularly elegant kind of collision. Like if these two carts have the same mass, then the blue one starts out moving, but then it stops. And then when the red one keeps moving, and then when it collides, it stops, right? So this very elegant kind of motion. Now we'll also look at a specific kind of wave, something called a standing wave. And a standing wave can happen if the wave that you're creating interferes with its reflection in just the right way. So I'm going to try and get something which is the right frequency to give me a standing wave here, right? So this thing is called a standing wave. And if you'll look, you'll notice the very center of the spring isn't moving at all, right? Whereas the two parts on either side are going up and down a lot, okay? This particular device is called a Wimshurst electrostatic generator. And if I turn the crank, these two discs are going to start spinning, and I think you'll see what happens here. I'll gradually build up more and more charge on those two spheres until you get these big bolts of lightning here, right? Those sparks there, in order to create a spark of that size, an inch or two long like that, takes about 100,000 volts. It turns out that when you have a current of electricity traveling around a coil of wire, it becomes a magnet. And so I can make a big current here. So here's 4 amps of current. That's a lot of current. But it won't even pick up this nail here. Well, it turns out there's something missing. What I need to do is take another piece of iron. So this is a piece of iron. It's not a magnet. It won't pick up the nail, right? But I'll put that iron inside the coil. And now when I turn on that current, now it's a magnet. And so it'll pick up this nail, right? And it's a magnet now, but if I turn off the current, it stops being a magnet. After doing magnetism, we're going to take a look at light. Okay? And what's neat about light is it really pulls together all the things from second semester. Because what light really is it's an electromagnetic wave. So it takes the things we've studied from waves and electricity and magnetism, puts them all together to get an electromagnetic wave. And what Einstein discovered, and he really found this mostly by thinking about electricity, magnetism, and light, was he found that the laws of physics as we thought we knew them aren't quite right. So one of those assumptions, for example, is that if you take an object like a meter stick, well, how long is the meter stick? It's 1 meter. And it seems like that couldn't be otherwise. Well, it turns out in relativity, the length of an object is not a constant property. The length of an object depends upon how fast it's moving compared to you. If something's moving relatively slowly, well, yeah, its length will seem to stay about the same. But if something moves very fast, now much faster than that, it actually has to move close to the speed of light. As objects start moving closer to the speed of light, their length actually changes. This meter stick would actually be shorter if it were moving very close to the speed of light. Okay? So that's a quick wrap up of all the different kinds of things that we'll study in our year of physics. Are you ready?